Section 1. Introduction into the Abyss, written by Neil deGrasse Tyson from the Hayden Planetarium at the American Museum of Natural History. Black holes. Just the name conjures up images of cosmic monsters devouring everything in their path. These enigmatic objects have captivated our imaginations for decades, inspiring countless science fiction stories and fueling our curiosity about the universe. But black holes are not just figments of our imagination. They are very real, and they play a crucial role in the evolution of galaxies like our own. Join me as we venture into the heart of these celestial wonders to unravel their mysteries. In this exploration, we will delve into the depths of space to understand what black holes are, how they form, and the profound influence they exert on the cosmos. Prepare to be amazed by the sheer power of these objects, where gravity reigns supreme, bending the very fabric of space and time. Our journey will take us from the death throes of massive stars to the edge of reality itself, where the laws of physics as we know them break down. Get ready to have your mind blown. Black holes are not just cosmic oddities, they are fundamental components of our universe, and understanding them is key to unraveling the grand tapestry of the cosmos. So, buckle up and let's embark on this exhilarating adventure into the realm of black holes, where the unknown awaits.
Black holes are born from the ashes of dead stars, cosmic entities that have reached the end of their life cycle. But not all stars are destined to become black holes. Only the most massive stars, those at least 10 times the mass of our Sun, possess the gravitational clout to undergo this dramatic transformation. As these stellar giants exhaust their nuclear fuel, they can no longer support themselves against their own immense gravity. The core collapses in on itself, imploding with unimaginable force. This cataclysmic event sends shockwaves through the star's outer layers, blasting them off into space in a brilliant supernova explosion. What remains is a core so incredibly dense that its gravity warps the fabric of space and time, creating a region from which nothing, not even light, can escape. A black hole. The more massive the star, the larger the resulting black hole. Stellar mass black holes, formed from these stellar collapses, are scattered throughout galaxies, silent remnants of once bright suns.
Imagine approaching a black hole, drawn in by its irresistible gravitational pull. As you get closer, you'd notice something strange. The black hole itself is not directly visible. Instead, you'd encounter a boundary known as the event horizon. This boundary is not a physical barrier, but rather a point of no return. Cross the event horizon, and you're forever trapped within the black hole's gravitational grip. No information, no light, no matter can escape back across this invisible threshold. The event horizon marks the edge of the observable universe, at least from our perspective. The size of the event horizon is directly proportional to the black hole's mass. For a black hole with the mass of our Sun, the event horizon would have a radius of only a few kilometers. Supermassive black holes, on the other hand, can have event horizons spanning billions of kilometers.
Section 4. At the heart of darkness, the singularity. At the very center of a black hole lies a point of infinite density and zero volume known as the singularity. Here, all matter that falls into the black hole is thought to be crushed into an infinitely small point. This is where our current understanding of physics breaks down. The singularity represents a fundamental challenge to our theories about gravity and the nature of reality. Einstein's theory of general relativity, which describes gravity as the curvature of spacetime, predicts the existence of singularities. However, it also predicts that the singularity is a point where the curvature of spacetime becomes infinite, something that physicists find difficult to reconcile with our current understanding of the universe. The singularity is hidden from our view by the event horizon, so we can only speculate about its true nature. Some theories suggest that quantum effects might prevent the singularity from becoming infinitely dense, while others propose that the singularity might be a gateway to other universes or dimensions.
Section 5. Seeing the invisible, studying black holes. If black holes are invisible, how do we even know they exist? Astronomers have developed ingenious techniques to study these elusive objects indirectly by observing their effects on their surroundings. One way is by observing the motion of stars. Stars orbiting close to a black hole experience intense gravitational forces, causing them to whip around the black hole at incredible speeds. By carefully tracking the movements of these stars, astronomers can infer the presence of a black hole and even estimate its mass. Another method involves observing the radiation emitted by matter falling into a black hole. As gas and dust spiral towards a black hole, they heat up to extremely high temperatures, emitting X-rays and other forms of radiation. By studying these emissions, astronomers can learn about the properties of the black hole and the material surrounding it.
Section 6. Cosmic whirlpools, black holes and their impact. Black holes are not just passive sinks, swallowing everything that comes too close. They are dynamic objects that exert a profound influence on their cosmic surroundings. One of the most dramatic ways black holes impact their environment is through the formation of accretion disks. As material spirals towards a black hole, it doesn't fall directly in. Instead, it forms a swirling disk of gas and dust, much like water circling a drain. These accretion disks can be incredibly hot, reaching temperatures of millions of degrees. The intense heat and friction within the disk cause the material to emit vast amounts of radiation, making them some of the brightest objects in the universe. In some cases, black holes can also launch powerful jets of energy and matter from their poles. These jets, traveling at nearly the speed of light, can extend for thousands of light years, influencing the evolution of galaxies far beyond the black hole's immediate vicinity.